It's not the size of the paper, it's what you do with it that counts. That's the way I look at it. Okay, so.
Your paper words are very, very,
Alright, so I'm still collecting myself because we have 12-dimensional pens. Oh my god, we got pens coming out of
Why
our
are they
ears.
12-dimensional?
Well, we're going to talk about dimensions, aren't we? When you say like 11-dimensional, what does that mean for something to be 11-dimensional?
There's
we don't
11.
know yet. Alright, so let's go back. Hold on. I'm starting the lecture already.
Does that mean doesn't that mean it's like 11 dimensions?
Yes. That's
But
exactly
what
right.
does that mean?
What is a dimension?
Yeah.
Exactly. So what we're going to talk about is, let's start with dimensions that we know. Like, what are some dimensional things that you know? Have you heard of 2D or 3D?
Yeah, of course.
Okay, so what's 2D? What's 2 dimensions?
Like flat.
Yeah, flat. Why are there 2 of something? What are the 2 things that there are something of? There's a one thing and then there's another thing. What are the 2 things?
Well, what do you mean?
It's 2 dimensions, right? Somehow a flat thing has 2 dimensions. What does that mean for something to have 2 dimensions?
Yeah.
Okay,
That's what I'm confused about.
Yeah, so how about we skip to 3 dimensions? A 3-dimensional object adds something, right? It adds, in addition to moving in these directions, you can move in this direction.
Yeah, like this.
Okay. All right, so let's go back to the 2-dimensional shape, and let's get a little bit more rigorous about it. One 2-dimensional shape that I know you know from Unity would look very much like this. It's a flat plane.
Yeah, from the side it's
Yeah.
that.
It's just that. It's a flat plane. But you can move around in the plane, right? You can't move in this direction, because that's not on the plane. You can't move in this direction, that's not on the plane. But within the plane, you can move anything you want. What's it typically called when you move in this direction in the plane?
X-axis.
The X direction, the X-axis, right. The X direction, that's all you need.
No.
What's it called when you move in this direction?
Y.
Y. Can we move in a third direction? Is there a third direction we can move
Yeah,
in?
Z.
Z. Can we move in that direction?
No.
Why can't we move in that direction?
Because it's 3D.
Because that would be 3D.
Yeah.
We're limited to 2 dimensions. So what are the 2 dimensions in the plane?
It's
X
X and Y.
and Y. Mathematically, we say this. We say, and again, remember, we're going to do this. I'm going to draw the line all the way to the right, because nothing we talk about in this lecture is going to be related to science. All of this is mathematics. What's the difference between mathematics and science?
A lot of stuff.
The fundamental difference is that mathematics does not have to apply to anything real. It can describe something that can't be realized really. So we're talking in the abstract world of shapes. A good example is, here's a plane. Can we have an infinite plane in mathematics where this number goes all the way up to plus infinity and all the way down to minus infinity?
Yeah, that's a line.
Yeah, it's like you can pick any point you want. How about in the real world? Could we have a line or a plane going out to infinity and down to minus infinity?
No,
Why not?
because the universe ends.
The universe ends. There's also another reason. You don't know this yet, but there's actually little bumps, kind of like the number line has bumps between 1 and 2 and 2 and 3. There's all these numbers in the middle that aren't defined, right?
Right.
Similarly,
Like 3/4.
yeah, you can't, if you're just talking about integers, none of those rational numbers
There's always
work.
a smaller fraction.
None of the irrational numbers in those intervals work, right? So there's another thing you don't know, and that is in the real world, distances are discrete, meaning distances jump. You can't have something between. The distances that you're jumping by are very short, but it's still almost like a number line. It's discrete. So that too is different. There's another difference. Can you ever really have a straight line in the real world? Not really. Einstein said the straight lines are boring. You can't really have straight lines.
No.
So there's very distinct differences between when we talk about the science side of things and the math side of things. When mathematicians talk about something, let's do this. I'm going to bring up a bunch of different cases. I'm going to talk about 0D, and I'm going to talk about 1D, and right now we're talking about 2 dimensions. Okay? We're going to go 3 dimensions, We're going to go to 4 dimensions. We're going to go to 5 dimensions. We're going to go to 6 dimensions. And then we're going to see if we can generalize, which means seeing if we can figure these things out all the way to n dimensions. So what's our kind of like our starter shape name in 2D? We said it was kind of like the plane. Right? Kind of a simple shape that just shows what it would, that space would look like is the plane. And then within that you could have things like squares or circles, but they would be
no 3D.
They would be finite. Right.
Like all of this is 2D.
Right.
It looks 3D, but it's not 3D.
Right.
It's all 2D.
Right. My point is that you have a space. You have like a universe, which is, mathematically speaking, infinitely far this way and infinitely far that way. It's just a flat, infinite plane. Within that, you could define regions that were interested in you. Like you could define the region that is a certain square, or the region that is a certain circle, or the region that is a triangle. Those are kind of like little pieces of that various space. But they too are flat or two-dimensional, because within them, there's only 2 directions you can move. So mathematicians talk about this in two ways. They say you either have 2 directions, meaning there's one direction that's perpendicular to another direction. So if you change this, it doesn't change this at all.
Right.
Okay? That term, the fact that something does, when you change it, doesn't affect the other one at all, is called a degree of freedom. You're free to change this without that changing at all.
So, like, here's y, and here's x.
Yep.
If we made the x shorter, like to here,
Yep.
there's this short, this wouldn't change at all.
That's right, unless we change the y value.
Unless we did manually change it to here.
Mm-hmm. Yeah, you could change the x value. Like if you have a point out here, you can change the x value to whatever you want. The y value is going to be the same. And then conversely, if you have another point, you can change the x value, and it's independent. You can change it. It's like a different knob. You can change the x here and the y there, and it's going to put it on the screen.
Okay, but my question is, if you have x and y and x and y, and if you change this y, will the other y go down with it?
Well, see, I don't know how you're defining those pairs. You have a pair of x and y's.
Like a rectangle.
You're not saying, oh, I see what you're saying. So, okay, yeah, here if you have this, this is actually a good thing to segue to, because this is actually what I was going to bring up later, but you brought it up kind of now. If we wanted to define a rectangle, we didn't really cover this when we did this in our lessons. Could we come up with an algebraic expression to define this shape? And let's say this shape and any of the interior points? We
area.
Could. What is the constriction on x and y?
The area.
We can have any x value we want subject to the constraint that what? x1 has to be less than or equal to whatever x value we pick, right?
Right.
This, we can pick that. We could put x right on top of that. That's allowed, right? But we can't go to the left of that, which would be x1 greater than x. That's not allowed. But as long as x1 is less than or equal to our x and also less than or equal to the right edge, which is at x2, then that's at, oops, I put the 2 in the wrong place, so it's going to make it x squared. So this is the basic constraint for x. And what this does is this actually defines a shape like this, going infinitely high and infinitely low. Right?
Right.
So what's a similar constraint if we wanted to constrain y? If we wanted to constrain y in this boundary, it would have to be at least y1.
Right.
At least y1 means this. y1 is less than or equal to y, meaning y is greater than or equal to y1. Y is at least y1. Right? And also we want that to be less than or equal to y2. So this defines this infinite shape here. And this first part defines this infinite shape here. Check this out. When we and the two, when we say this and this has to be the same, and this is just the mathematical symbol for and.
Which means...
You can think of that like the letter A minus the little thing in the middle.
Yeah, like
that means and.
Yeah.
So the points, but we say that the locus, the set the collection of points for which this is true and this is true is this. What I would like you to do now is go get your iPad, fire up Safari, or did we ever load Wolfram Alpha on it? Let's see.
Yes, we did.
Load Wolfram Alpha, that'll make it easier. Don't trip on the power cable of learning.
Yeah.
But no, bring it back here. Bring it back here. Bring it all back here.
It's 28%. That's okay.
Well, we got power right here.
Yeah, but it's okay.
So you're going to go to Wolfram Alpha, and you know what you're going to say? Let's look at each of these. Pick a concrete value for x1 and x2. What I mean by a concrete value is give them actual numbers. What's x1? Give it a number.
7.
7. And what's x2? Give it a number.
9.
9. And what's y1?
10.
10. And what's y2? It has to be bigger than y1, obviously.
39.
39. Okay, so try this. Try just the first part of it. X1 is...
Wait.
7.
What do I do?
Well, look. Here's the first shape. The first shape we want to do is this vertical shape here, right?
What should I type in, though?
Well, I'm explaining. In the general case, when x1 and x2 are not fixed, the equation would be x1 less than or equal to x less than or equal to x2. All we're doing here is x1 is 7. So you're going to say this. You're going to say 7 is less than or equal to x. And you may have to do it this way because you don't have the less than or equal on the keyboard. And that has to be, less than or equal to 9.
I have less than or equal.
You have less than or equal? Well, then use it. Use it, my young man.
Okay.
So look, this is what, it got messy. Let me do it again. 7 is less than or equal to x.
7
And that's less than or equal to
than
9. So you're doing that.
or equal to...
This is it away.
Okay.
7 is less than or equal to x, less than or equal to 9. 7 is less than or equal to x, and x is less than or equal to 9.
Equal to
9.
9.
Yep. And you say enter. No. 7 is less than or equal to x. You got to syntax.
7.
Didn't you say you had a less than or equal to something?
Less than and equal.
Oh, okay, okay.
7 less than or equal
To x.
to x.
Yeah, I think you left out the x part is the problem. And then that's less than or equal to 9.
Less than equal to 9.
Yeah. Get rid of that keyboard. I want to see it before you punch it in.
How do I?
There's a keyboard symbol there. Yeah. 7 is less than or that should work. Yep. Except you want to hit the yeah, you want to hit the the equal sign. Maybe not.
Maybe go?
Maybe
No.
maybe your iPad sucks. Hold on. Maybe,
My iPad does suck.
Go. Let's try it. It's going. See, it's only showing you it's showing you on the number line the way it would be. But that's actually this shape. Imagine you're taking this and moving it this way, because y is unconstrained. Right?
Right.
Y can whatever. So it's this shape moved up and down. Now do this. Now add after that add space. Yep, space. Which is probably,
hang on.
I don't know, because your thing, it's all messed up with that split keyboard
Okay,
view.
space.
Yep. You type the word and, A-N-D, space. Now we're going to put in the y equation. Here's the y equation. y1 is 10, right? So 10 is less than or equal to y, which is less than or equal to 39.
Y, which is less than equal to 39. Go.
Now, what shape do you expect? What shape do you expect to emerge?
A rectangle.
That's right, and
A
it's
square.
showing you exactly. No, is it a square or a rectangle? What's the width of the bottom?
Oh, 9.5.
The width of the bottom is 9.5? No. What's the width of the bottom?
What do you mean?
What's the width of this side here? It's from going from 7 to 9. So what's the width of the bottom?
Oh, 2 whole.
2. Right. And what's the height of this thing?
10, 20, 30, 40, 40. Or no.
It's actually 29. The difference between 10 and 39 is 29, right? So it's 29 tall and 2 wide. So why is this not a square?
It says 40 tall.
No, the numbers go up to 40, but remember the first 10, it only starts from 10.
Oh.
See, the numbers go up to 40. So this is very close to where the top is. But if you subtract these 10, then it's closer to 30. And it's not quite 30 because you said it started at 39.
Yeah.
Right? So why is that not a square?
Because these aren't equal.
Right. They're drawn equally in the graph, which is misleading, but they're not equal. Right? So that's just the way that's drawing that. Okay, so here's the point. We just learned something about 2 dimensions. What are the names of the dimensions? We have x and y, right? So the dimensions are x and y. And one of the simple objects we could do would be to create a rectangle. And what's the formula for a rectangle? It would be this general formula, right?
Right.
We have x1 ranging from some lower bound, call it x1, up to some higher bound, call it x2, and y1 is less than or equal to y, less than or equal to y2. So you see how this algebra here, and let me show it to the audience. That,
they're recording.
oh, of course. That is the algebraic way of saying this. Do you see how this is kind of like the logic? This is saying one of the constraints is that x can only be between these 2 bounds. That's like that vertical thing we were talking about.
Right.
The other constraint is that y has to be within these bounds, which means it has to be a band like this, right? Where is it that both of those things can be true? Well, you literally take those 2 bands and you find where they overlap, and that makes your rectangle. Where this is true and that is true, it's a rectangle. That means x has to be within those bounds and y has to be within those bounds. And then you have the rectangle. Okay? So algebra is a way of assigning a logical way of thinking about it. This is the pictorial way. It's good if you get used to doing it both ways. Okay, now let's start to talk about the geometry.
What is ND?
N-dimensional. We're going to put in things here that it's going to say, for n dimensions, how do we talk about these things?
Oh, okay.
Meaning 100 dimensions, 1,000 dimensions.
A million.
You'll see a million dimensions. You'll find it's not that hard once you know how to generalize the pattern that we're going to see. So we're just talking about 2D. The basic object where you just allow it to go out to infinity in all directions, that's called a plane. Okay?
Right.
The dimensions are x and y, and when we restrict the bounds of those dimensions to fixed lower and higher limits, then it becomes a rectangle. Okay? Or in the strictest sense, if the width and the height were the same, we'd call it a square. So let me say that a square would be one way of saying it if it was equal on both sides. Okay? Now let's count the number of vertices. How many vertices are there in that shape right there on your screen? You remember what
4.
a vertex is? Yes, a vertex is a corner. How many edges?
4.
4. How many faces?
1.
1. The face would be the face, the area facing you. How many volumes? You don't really know what a
0.
volume is
yet,
yet, but 0. A volume would be a 3-dimensional shape.
Yeah.
Okay, would you like to go 1 down in dimensions or 1 up in dimensions for the next one? I'll let you guide.
1 down.
1 down. Okay, if we're talking about a 1-dimensional thing, what are we talking about?
Lines.
A line. Or, I'll show you, it could actually be a curve. So we have a line, and this right here, plane, could also be a surface. We'll get into that in a minute. there's nothing when you say it's one-dimensional that says it has to be. As long as it yeah. Let me not get ahead of myself. We're going to talk about this. It's definitely a line can be one, but in general it could also be a curve shape, and I'll explain why. What would be the dimensions? Names of dimensions. So in a 1D shape, what directions can we move in? Can we move in the Z direction?
No.
Can we move in the Y direction?
No.
No.
Just the X.
Just the X. So we can go to plus infinity on X and we can go to minus infinity on X. So X is the only dimension that we can move in, right?
Right.
Okay. And if I gave you, we can similarly set something up where we have a fixed range where it would fall in, like x1 is less than or equal to x is less than or equal to x2. Do you know what that shape would be? So if x is between two fixed boundaries, x1 and x2, do you know what we would call that? We have a name for it.
A line segment.
A line segment, that's exactly right, because it's finite. What about if I said x1 is less than or equal to x? What would be the difference there? If I left out the less than or equal to x2. Should we try this? Let's try it.
Okay, yeah.
Okay, so if I simply said there's no constraints, we have a line, right? Because the line can go from plus x to plus infinity to minus infinity, right?
Right.
Okay, so if I said here, x1 is less than or equal to x, and that's less than or equal to x2, we know already that's a line segment. Oops, I shouldn't have drawn that whole thing, but whatever. That's a line segment from here to here, and all the points in between, and those endpoints, because I said less than or equal. So because of the equality, those endpoints are in there. Okay, what about if I left this out? x1 has to be less than or equal to x. What shape are we looking at? Or another way of saying that is x has to be at least x1.
Still a line segment.
Nope.
No?
Because is there any mention of x2?
No.
Yeah.
Array.
Array, exactly. So this goes from x1 and is now in this direction like this. So this is the equation for array. This is the equation for a line segment because there's two constraints. No constraints, and you have a line. If the value of x is arbitrary, then you say you have a line or a curve that's infinite. It's getting interesting, huh?
Yes.
So this would be, like you said, the equation for a line segment. And how many vertices does a line segment have?
2.
2. And how many edges?
1.
And how many faces?
None.
And how many volumes?
None.
Should we talk about, okay, do you want to go 1 up to 3D,
I'm
or do
curious
you want to
about
go to 0? Do you want to go to the zero-dimensional world?
Mm-hmm.
Okay.
That's nothing, right? It's just...
Well, I think we have to look at it a little differently to describe this. A lot of the way people talk about this is to start with 0 dimensions and work up. And I'll just say that a zero-dimensional object is simply a point, because in all of these, we're going to start with a certain initial shape and then do something. Our initial shape is just a point to begin with.
Right.
We're done. That's a zero-dimensional object. How many directions can you move in? I haven't given you any directions.
Infinite.
So there are no directions for you to move in because I haven't defined where the axes are or anything. So
right.
A zero-dimensional object says you're at a point and you can't move anywhere. You're done.
You're stuck.
Yeah, so the only zero-dimensional object is a point. Doesn't matter where you put it, it is a zero-dimensional object.
That's why everything's 0. 0 volume, 0...
Yeah, there's just...
edges,
yeah.
0 vertices.
So, whereas this was a plane or a surface, and this was a line or a curve, the zero-dimensional thing is called a point.
Point.
And what are the names of the axes that it can move in? This was x, y, and this was x. You lost the y. So
Then nothing.
There are no. Yeah, it's the null set.
Blank.
There are no. Yeah, there are no axes you can move in. It also doesn't make sense to put in an equation to do these because a point is a point.
Right.
How many vertices does a point have? Here,
None.
I'll show you the picture.
One.
One. The point itself is a vertex. How many edges?
None.
How many faces?
None.
None. How many volumes?
None.
Now, watch this. I'm going to show you the other way of constructing this. What we now do, using the red pen.
Ooh, can I use the red pen?
Yeah. Is we're going to. I'm going to introduce a direction called the X direction. What I'd like to do is you, with this infinitely thin Sharpie there, what I'd like you to do is start from here and move 1 unit in the X direction, this way. So just draw that movement in 1 unit my way. What do you think 1 unit is? It doesn't really matter. Make it a bit wider than that. That's a beautiful 1 unit. So what you just did is you drew 1 unit into the X direction. What we now do is we take whatever we started with, we clone it and we put it here. So where we started with 1 point, we now move, we translate that point 1 unit over, and then we just draw the edge between them.
That's 1 unit.
This is now how many dimensions?
2.
It's a line segment.
Why is it? Oh.
It's a line segment, right? We started out with 0 dimensions. We added this dimension.
Right.
So now we're at 1 dimensions. This is a 1-dimensional object. It's just a line segment, right?
But I thought it was second dimension because second dimension is 2D.
Second dimension is 2D, but where's the two directions?
Second dimension is a...
Where's the 2 directions that you can move in? We know you can move in X. Where's the other one?
Oh, yeah.
There's no Y or Z.
Oh, it's 1D, though.
This is 1-dimensional. So this is a line segment, and we see, look, we have 2 vertices. We have 1 edge, just like we expected. Now here's where it gets really fun. You're going to take over on the blue pen as soon as I draw something, and I'm going to do a red thing.
Okay,
So